Um, as many of you may not be knowing, he is one of my old friend. So today I'm going to talk on theoretical chemistry, a tool for chemists in the new age. So basically, what I will try is to give you a flavor what theoretical chemistry is, how different it's from theoretical physics, and what is actually computational chemistry, how it is different from a theoretical chemistry. So we are going to touch in this aspect. So I am now currently in the Indian Institute of Technology, Bombay, which is on the west coast of India. So it's different time from the total west. So it's still not very dark here. It's outside still light. Sunset generally happens pretty late here. And this is the iconic arch of our institute, which says our motto, and that is Jnanam Param Dhyam. So knowledge is the supreme quest. So that's what we try to find here. We are in Bombay, and the moment you talk of Bombay, the things which comes into your mind is crowd and tall high rises. Although in these days Bombays are in news for different reasons, but our campus is actually very green, situated on the verge of Powai Lake, and we also have our share of wildlife. So you see crocodiles in the waters of this Powai Lake, and leopards are a regular visitor to our campus. Although these pictures are taken from internet, the leopard regularly comes there. As far as I know, it was there in yesterday also. So we have an interesting life here. So I'm going to talk mostly on the areas of theoretical chemistry. Now, the moment we hear the word chemistry, things come to our mind is chemical labs, shoot, dust, and smell. But what I pursue personally is a different branch of chemistry. It's called theoretical chemistry. That means trying to model the chemical processes by mathematical formulas. And we chemists are not very fond of mathematics. It's that something we try to avoid most of the times. And when theoretical chemistry started, many of these traditional philosophers thought that it's not the correct thing to do. And one of them is this French philosopher whose name I cannot never pronounce. He said that any attempt to use mathematical methods for the investigation of chemical questions must be considered as completely irrational and is strongly opposing to the spirit of chemistry. If mathematics will ever occupy a prominent place in chemistry, an absurd idea that fortunately is completely unrealistic, this would lead to a rapid and irreversible decay to this discipline. So mathematics has no place in chemistry. And what we are doing here? Well, he has been proven wrong within 100 years by these three gentlemen. Erwin Schrödinger developed wave mechanics, Werner Heisenberg developed matrix mechanics, and Paul M. Dirac actually married the quantum mechanics with the theory of relativity. Now, one interesting thing to notice is that all three of them are Europeans. Schrödinger is an Austrian, Heisenberg is German, and Paul M. Dirac, he actually belongs to UK, United Kingdom. So quantum mechanics was essentially started by Europeans. Now, the advantage of using quantum mechanics is that to solve the Schrödinger equation does not matter. It's a book or a chemical molecule or a building. If you can solve the Schrödinger equation, you know everything about it. There's no ambiguity. Although we always call Schrödinger equation for all practical purposes, for all the chemical compounds or chemistry problems, what is solved is actually Heisenberg's formulation of matrix mechanics. We call it a Schrödinger equation, but what we solve actually is matrix mechanics. That I sometimes find funny. And this is one of the very well-known quotation of Paul Dirac. He says that the fundamental laws necessary for the mathematical treatment of the large part of physics and the whole of chemistry are thus completely known. The difficulty only lies in the fact that application of these laws leads to equations that are too complicated to solve. So the theory is there. The problem is that if you apply those theories, you get very large equations, which you cannot solve. So that's the problem. And the less known part of this quotation, which goes on to say, hence it would be desirable to develop practical approximation scheme for the application of quantum mechanics. That means quantum mechanics cannot be applied exactly. You need to take practical applications. approximations. Now, many people think that this statement is the birth of the so-called quantum chemistry or the theoretical chemistry. Well, I beg to differ with them because Paul M. Dirac was a physicist. He was not a chemist by any means. The quantum chemistry actually started with the arrival of Linus Pauling. He's a very curious character, has a great contribution to the chemistry. He is one of the very few chemists who actually won 2 Nobel Prizes, one for chemistry and one for peace. And his contribution to the chemistry is immense. Electronegativity, concept of hardness, structure of ionic crystals, biomolecules. But his most celebrated work is on molecular orbital theory of chemical bonding, where he shows that the 2 hydrogen atomic orbital gets combined to give a bonding molecular orbital, and if the electron goes there, it forms a bond. It makes the molecule stable, and if the electron goes to the anti-bonding orbital, it's leads to slightly unstable. So that's not stable. So this is the molecular orbital theory of chemical bonding. Now, don't get confused by sign plus or minus. They have nothing to do with the charge. They are just phase factors. Now, the first book on actual quantum chemistry actually came out in 1935. So this actually marks the birth of quantum chemistry because this is the first book, Introduction of Quantum Mechanics with Application of Chemistry. The book is still available in Amazon if in case some of you are interested. Now, this molecular orbital diagram has many of us, those who have a chemistry training or have read some chemistry, have seen in our textbooks. Now, this molecular orbital theory you can only solve for diatomic molecules and sometimes for some triatomic molecules provided they have enough symmetry. But if the molecule is bigger, larger than that, and if they don't have any symmetry, unfortunately the equation, as Dirac said, becomes so complicated that you cannot solve them by hand. But the problem some solution to the problem came with the advent of computer. And we all of us know how computer works. In actuality, computer is actually a very stupid machine. It only understands 0 and 1. Believe me, it does not understand anything more than 0 and 1. And these are, they call these truth tables. From 0 and 1, these are logic gates. So between you give the 0 and 1, and between what kind of operation you are using, it gives you a result. It just knows that. Everything else, the input and the output, the input has to be given by you, and the output has to be read by you. So don't think that computer is a smart machine. It's just a stupid machine. How smart the computer appears depends upon who is using it. So this is so-called the mechanical logic gates, how it originally started. And this is what a modern day supercomputer looks like. So this is the supercomputer there in IIT Bombay. It has a peak computing capacity of 1 petaflop. So it's almost 10,000 times faster than your desktops. And advent of computer has made the calculation possible for molecules which are not small. And in our life, many of the molecules which we are interested in are not small. So because of this advent of computer, what was become theoretical chemistry now has turned to computational chemistry, where you use computers to solve this equation. And this is the so-called Moore's law, which roughly says that in each 2 years, the number of computer chips you get in a place actually get double. At the same time, their price actually get half. So this curve actually shows time versus how many calculation you can do per second at a cost of $1,000. So when it started in 1910, 1915, where there were analytical engines, you cannot almost do a single calculation in 1 second for $1,000. And in modern time, you can do 10 to the power 10. If you go to see in 2015, the i7 computers, they are super fast. And in our lifetime only, we've seen the computer to change so much. Some of you who are from my generation have probably seen these floppy disks with 1 MB space. Then it comes DVDs, CDs, then DVDs, and nowadays you get hard disks with terabytes of space at a throwaway price. So now with the advent of modern and faster computers, it's possible to treat more and more complicated molecules. Now the computer was not enough. It was required the man. And here comes the man, Sir John Popple, who actually started to use those computers to write computer codes which can do calculations on molecules. And he is the first person to develop a software which can be used by non-experts. And his first software is known as Gaussian 70. So his program used to use Gaussian type of function. That's how the name comes, Gaussian. And Gaussian is still very popular. Some of you may have used it. This is the first version of Gaussian. It was written in Fortran. So you can see in the background, the punching Fortran codes. And you see in this slide, there is something called QCP. It's the software was available through Quantum Chemistry Program Exchange. That is QCP there. Now, John Popple, because of his contribution, he won Nobel Prize in Chemistry. Now, that is something very surprising because theoretician winning Nobel Prize in Physics is very common. Many of the quantum who have started quantum mechanics, actually all of them, Heisenberg, Dirac, and Schrödinger, all three of them have won Nobel Prizes. But for a chemist to win Nobel Prize, doing theory is very peculiar. And 1998 was the watershed year when Sir John Popple, along with Walter Kohn, actually won the Nobel Prize. Now, this initial version of Gaussian was freely distributed through Quantum Chemistry Program Exchange. So it's a free software. Anybody can use it. Anybody can see what is inside. When things becomes a little bit more interesting, so one of his students went on to make a startup company called Gaussian Inc. And Gaussian Inc. from 1987 started distributing license. But what was free and open source, now Gaussian start to pay for a price. Okay, the price part is fair enough. He has to run a company, so he needs to have the money. But at the same time, he stopped people from giving the source code. So now nobody can see what is inside the software. It's a black box, easy to use, but you don't know what is inside. So, and at the same time, he actually started banning people from using the software. Whomever he used to think as his competitor, the company just started banning the software, and it even banned St. John Popple, the very man who actually started the software. It's a curious case. One of the student of his started a company, taking his permission, his license, and after a few days, he started banning him, the teacher himself. So it's a sad case of marketing monopoly and the money winning over the trust and the nature for science. Now there's a lot of the people who are actually interested towards development of computational chemistry, the program packages. Those who Gaussian company thought as their competitor, they started banning it. And that's how the name came banned by Gaussian. So many of the eminent theoretical chemists whom the Gaussian think them as their competitors, they are banned by Gaussian. So they cannot use the Gaussian software like others. Although knowledge can never be stopped from banning. So in place of Gaussian, many other quantum chemistry software came up. You have Molcus, you have MolPro, TurboMol, QChem, PQS, Orca. So to name of the few. If you go to Wikipedia and search with quantum chemistry software, I think you will get almost 99 or 100 softwares are there. The software which I listed are more popular and actually is quite general purpose to use. Well, question is what we can calculate with this software. So Enrico Clementi, one of the pioneering man in this field, in 1975, he told that we can calculate everything. So give me a molecule, I can calculate everything about that. Now, Enrico Clementi is born in 1931. He's still alive, 90 years old. I had the great fortune to meet him once. He's a very charismatic man, but I think what he made is an overstatement. Like at the beginning, what the philosophers said is not true. What Enrico Clementi said is also not true. No, we cannot calculate everything. Even after 45 years of his statement, also we cannot calculate everything using computer. But we can calculate actually a lot of things. So what we can calculate? We can calculate or predict quantities which cannot be measured. If your reaction is happening very fast and your reaction intermediates are very short-lived so that you cannot trap them using any experimental method, In computational studies, you can understand how the reaction look like. Sometimes you take a spectra and you don't know why the peak has come from. So in that case, you can use the computational chemistry to understand what gives rise to the peak. You can find trains in the regularities in the data. Many of the times we know the certain kind of compound gives certain behavior. You use computational chemistry to find out why they give you certain behavior. And also you can predict a future experiment. So in present time in drug discovery, many of the cases, it's first computational study where they can screen the possible drug candidates and then they do the actual experiment to do biological trials. And that's also getting used for the recent drug development for COVID studies. But at the end, theory and experiment are not something separate. It's a synergy between the two, which actually can help you to understand the chemical process better. Okay, let me give you an example. So this is a real life problem. So Friedel-Crafts acylation reaction, generally taught in undergrad chemistry. So one of my friend, Dr. Sumanta Garai, I was still a PhD student in NCL Pune. So he was trying to do Friedel-Crafts reaction, acylation reaction using ester. Now in all the previous reports, it was shown that the reaction go through the anhydride carbonyl groups. What he was getting, the product what he was getting, like predicts that the acylation in his case goes through the ester carbonyl group. Now he suggested some mechanism that there first a carbocation is formed and through that carbocation then reacts with the benzene to actually go the Friedel-Crafts acylation reaction. Now don't ask me about the reaction mechanism in any details. My organic chemistry is always very poor. That's what he told me. So, but his problem was that he does not have any support for his mechanism. His intermediates cannot be isolated. So he does not have any proof. And moreover, he was not sure what mechanism he was proposing was correct or not. So basically we were sitting one day in the afternoon actually drinking tea, and then we decided that we'll do something together in that. So we actually did a modeling of the structure and we calculated called reactivity descriptor. So this guy is famous, is Inochi Fukui. He is famous for this description of frontier molecular orbital, and what it gives is reactivity descriptor. So you can give numerical numbers to centers, so which is more reactive and which is less reactive. In this case, among the anhydride center and the carbonyl center, we found out that carbonyl center actually has a higher value of the Fukui functional. So the reaction should proceed through that. And then we go on to find out the transition state theoretically. And we found out that the transition state which goes through the carbonyl carbon is actually much stable. And the transition state which actually goes towards the anhydride carbon is actually 36 kilocalorie per higher in energy. So the reaction cannot proceed through that. And you can only get the product when it goes through the carbonyl carbon. So we have a wonderful paper out of it. But this shows you how theory and experiment can show you how a chemical reaction actually happens. Because only theory or only experiment just give you half of the picture. It does not give you the full picture. If you use both of them together, you can get a complete and a full picture of the chemical processes. Now it was a small molecule. Some of the times you are interested in larger molecules. Like this is the active site of photosystem looks like. Of course, you see a big structure. It's oriented in a particular way. And that's what the nature did. Nature did for million years of evolution to arrive at this particular structure, which is most optimized for energy conversion. Now, if I want to study this kind of system, I cannot really use the methods which I was using for study of the small organic molecules. So I have to come with different molecules. And that gives you a picture about what kind of methods you should use to study different kind of problems. Suppose you are, and that's called a length scale thing. If you are interested in length scale of nanometer, you want to understand phenomena which happens in a nanometer length scale, like breaking or making of bonds, chemical reaction, you should use quantum mechanics. If you are interested in the micrometer phenomena where orientation of molecules, folding of proteins, you should go to molecular dynamics. And if you are interested in millimeter phenomena like flow of molecules, which mostly engineers does, then you should go for macroscopic methods. So depending upon what kind of problems you study, that depends upon your choice of problems. In chemistry, most of the times we are interested in nanometer phenomena because chemical bonds, they are basically happens, bond breaking and making basically happens on that time scale. But it's also true that there are many interesting phenomena which actually happens in the junction of the so-called quantum mechanics and the molecular mechanics atomistic simulations. Because many of the biological processes, the enzymes, they actually makes and breaks bond. But although they makes and breaks bond, they are not small molecules, they are much larger. So to get the accuracy, you need to use quantum mechanics, but they are too large to use quantum mechanics. So somehow you have to make a compromise. And that recipe is given by these three strange looking gentlemen. They are the second time they won their Nobel Prize in 2013 for developing the so-called QMMM method, which is a hybrid between a quantum chemistry and molecular mechanics. So you can study properties which are intermediate of these two length scale. This is Martin Karplus, is Michael Levitt, and Aya Warshall. So these are the second time with the history of chemistry, theoretical chemist actually went to one Nobel Prize. So what this method actually do? So it separates the entire compound into two parts. We know that in enzyme also there is an active site. So the active site you can treat in a quantum mechanical model. The surrounding environment you can treat in a molecular mechanics where less accuracy is required. And then you can treat the overall system in a mixed method where one part is treated in a high level quantum and the other part is treated in a low level molecular mechanics method. So this kind of QMM studies are very important if you are interested in biological molecules. We are going to see some examples of that. But just to let you know which software you can use to do this kind of calculation, quantum and quantum mechanical. So my personal favorite is Orca. So Orca is actually Orca means killer whale, but this is the name of a quantum chemistry software. I am one of the developer of this software. So it has DFT and it can do DFT and wave function based calculation. It can do QMM based calculation. It can do molecular dynamics, and it supports a wide range of spectroscopic calculation. It allows simulation of UV visible, NMR, EPR, X-ray, MCD, many of the spectroscopic properties you can calculate. And best part of it is that unlike Gaussian, which is a paid software, this can be used for free. And it's quite fast. You don't need a supercomputer to use it. You can just install in your desktop. It supports both Windows and Mac and Linux also. And you can do these calculations yourself. So let us see an example where this kind of things are important. This is a very famous example of a DNA double helix. So you can see the structure where your DNA molecules, these nucleobases are inside, and on the outside you have the sugar phosphate backbone. And this particular arrangement actually carries the secret of life. It's a genetic code. And molecular modeling has been always an integral part of DNA. Don't forget the structure of DNA by Watson and Crick was actually developed by making models. So from the model they found out it actually has a double helix structure. Now what happens is that when we use high energy radiation on these DNAs, they actually destroy the DNA. So one of the direct ways to have, and we have seen many examples, very common example is that if you go out in the sun. If you go out in the sun, if you are you are an Indian or from a country where the skin color is not so white, then your skin will get tan due to melanin. But if you are from the Caucasus region and have a white skin, if you go out in the sun, you will see that your skin will start to peel off. And that's why people use sunscreen when they go out in the sun. Because of the fact that high energy radiation actually destroy the DNA and it leads to cell death. So how the cell death actually happens? One way is that it directly knocks out electron from the DNA, so the DNA dies. But also it's true that in our body there's a lot of water. So when this radiation struck this water, the electron comes out. And this aqueous electron, this aqueous electron reacts with the oxygen present in the body to generate these free radicals. And these free radicals attack the DNA to break down the DNA. And when the DNA breaks down, the cell cannot divide anymore. So the cell dies. And presence of oxygen is actually essential for this destruction mechanism. That's important. But this is something an evil where it can be used. But we know that, so that means this radiation can stop the DNA from replicating and then it damages it. But this is also used in the cure of cancer. And cancer is one of the major challenges the mankind is facing in the recent times. And cancer is not a new disease. I encourage all of you to go through this book of Siddharth Mukherjee, The Emperor of All Maladies, which describes the history of cancer. And cancer is not a new disease. It's known from the Greek time. And the main manifestation of cancer is uncontrolled cell growth. So your DNA starts to divide so quickly that it does not remain controllable, and then it leads to a disease, cancer. So that means that this radiation, which destroys actually DNAs and leads to cell death, can be used for the cure of cancer. And all of us know is the radiation theory is one of the commonest form of cure for cancer. Well, problem is that this ionizing radiation used for cancer cure not only kills the cancerous cell, it also kills the normal cell. And because of that, if you undergo radiation therapy, there is always a risk of early and late side effects. Many of the times there's a lot of side effects on the cancer patient, including development of secondary cancer. Don't forget that Marie Curie actually died of bone marrow cancer because of the highly radioactive compound she was dealing with. So the radiation, although it can cure, can also cause cancer. So we have to find out a way that the radiation only attacks the cancerous cell, but not the normal healthy cell. More problem is that you have to use high dose of radiation because our body repair mechanism is so smart that many of the cell damages, what the radiation damages, the repair mechanism automatically repairs it. That's why even we go out in the sun, we don't die, because most of the damage happens, the body mechanism actually repairs it. So to actually destroy the cell, we need to use a high energy of radiation, but that's also very disastrous to normal cell. And that is particularly problematic because cancer cell usually suffers from hypoxia, which is less oxygen. And what we see in the radiation damage process, it was the presence of oxygen which leads to those radicals which actually destroy DNA. So cancer cell, the situation is bad because there is no oxygen, so there is no free radical, so it cannot be destroyed much more easily. So the treatment is to thus go for so-called radiosensitizer. So what is actually a radiosensitizer? So radiosensitizers are compounds which actually absorb this aqueous electron in place of oxygen, and then they lead to free radicals which attack the DNA. Something like this. So this is 5-thiocyanodioxide radiosensitizers. If you put the radiation on it, it takes up an electron from the water, and then this free radical generate, it attacks the DNA, and then it breaks down the DNA. And that's, so for cancer cell where there is no oxygen, you can actually give this radiosensitizer compound as a drug. So these radiosensitizers get accumulated in these cancerous cells, and when the radiation falls on it, they breaks down to give you the radical which actually destroys the cell. But remember, all the drugs are actually poison, and many of these radiosensitizers actually has a lot of side effects. So to develop new and effective radiosensitizers is a very active field of research, and theoretical chemistry can help you to understand which compounds can be used as a good radiosensitizer. To act as a good radiosensitizer, okay, it first need to have two properties. First of all, it has to accept an electron, because remember, if I go back, it was the aqueous electron which was reacting with the oxygen, or in this case with radiosensitizer. which was reacting to give these free radicals getting which were destroying the DNA. So it's the low energy electron which actually is causing the cell death. So to have an effective radiosensitizer, we need to have compounds which has a very high electroaffinity, and it should quickly dissociate after absorbing the electron. And second thing is that it should be less toxic. So it should not attack other cells or create toxic reactions in this in our body. So currently this kind of compounds are very limited, but theoretically to screen this kind of compounds which can be act as a radiosensitizer, you need to develop new methods which can describe electron attachment to atoms and molecules. So the currently available methods, they are not good enough or they are not accurate enough, which can give sufficiently predict which compound can be good drug and which compound is not. So large part of my group research is actually based on that. And so there are a few recent papers which we have published on these topics. So this is my group at IIT Bombay. This was in last winter when the social distancing was not necessary. Now the campus is totally empty when my students are not there, but this is how the group generally looks like. One can join the group as PhD student. We have a very comprehensive PhD program in IIT Bombay, which allows you exposure to a lot of the field, also allows sponsors to attend one of the conferences abroad. We have a very good postdoc scheme, which is very competitive and very well paid. And also IIT Bombay offer paid intern for 6 months. So these are the ways you can join our group and help in our research. We need both chemists and as well as programmers, because we develop the software and as well as use for this quantum chemistry application. Okay, so up to now, what I have talked to you, how the quantum chemistry started as a branch of quantum mechanics, how it went into chemistry, how quantum chemistry became computational chemistry with the advent of computers, and how it can be used to solve real-life biological problems. Now, I want to spend at least a minute on how the future looks like. So in recent years, the growth of two things, artificial intelligence and quantum computers, actually has changed the landscape a lot of. So, these days, because of the artificial intelligence, many of the things which were human made, now the machines itself can do. You try to make a spelling mistake in Gmail, the Gmail automatically corrects it. It can even prompt you the name of the sender to whom you are sending. So that's what the artificial intelligence is. But in chemistry, it can have a lot of impact. Like many of the reaction mechanism, we draw that, okay, arrow will go in this way, it's electrophilic reaction or substitution. That comes from our experience. That's our mind processing data. Now, artificial intelligence can process data much more quickly and more efficiently using computers than human mind can do. So many of the things which we are doing by hand or by just guessing, now computers can predict it much more accurately. Second thing is quantum computers. A normal computer, as I said, it only understands 0 or 1. It can be 0 or 1. Quantum computers can be 0 and 1 at the same time. This is the IBM quantum computer. And because of the development of quantum computers, many of the calculations which we thought that is not possible takes hundreds of years, now it will be done in minutes and hours. So now it opens up a doorway that many of the reactions what you practice in lab does not need to be performed. You can actually do a quantum chemical calculation on them and predict them what will be their outcome. So many of the reactions will not be necessary to do. But that does not mean that involvement of human beings will get reduced. It's computer, be it's a quantum or a normal computer or the artificial intelligence, it's finally at the end of the day, it's a stupid machine. The artificial intelligence only works on the training sets you develop, how you well train the computer, and that training has to be done by a human being. Also in quantum computers, all the computers program which were existing for the traditional computers will not work in a quantum computer. That means a lot of programming, computational software rewriting has to go on. So there will be a need for a lot of trained manpower. So any of you who has interest in artificial intelligence and quantum computing will have a bright future together. Okay, so this is up to what I wanted to say. In the acknowledgement, I want to thank Department of Chemistry, JIS University, for giving me this opportunity to speak here. I want to thank my friend Professor Parthapatim Ghosh for this opportunity. Of course, my students. So whatever work I shown, it was actually done all of by them. I just only shown them. And of course, the funding agencies, IIT Bombay, DST, and Inspire Fellowship for the money I get to set up those facilities. And of course, all of you for your kind patience to assemble in a Sunday afternoon and to listen to my talk. Thank you very much for your kind attention.
One question can we put?
Sure.
Okay.
Sure, go ahead.
Really deduct quantum mechanics, bracket notation and Coulomb quantum variant, and actually, can we differentiate at present, there is quantum chemistry or quantum physics, can we differentiate? Actually, quantum concept is interdisciplinary subject, So it cannot be, I think, even if you have told that, they actually study the characteristics of the cancerous cell or other cell or complex compound also. It is in EPR, mainly in the cultivation of science, I already been there. So, sensitizer, it is a process of actually media of cancer, but it is not being under process, I think, because it is being observed that there is low temperature in the Kelvin order, the characteristics of cancer cell the characteristics is somewhat different. So that we have predicted, that we have concluded, but it is not actually ultimate. So that's why it is prediction. So this is the question. I think you will explain everything at the subject in expanding this subject. Next one thing, I have a very interesting thing. There is artificial intelligence. There is brain computer interface, etc. How can we actually the computer makers a computer quantum computer can be connected? This is the main way because may very curiosity, So there is I understand the quantum concept, quantum computer. No. How can you connect this in artificial intelligence? This is my question.
Okay. So let me try to answer one by one. First question I think was that can we separate between quantum physics and quantum chemistry?
Right.
So it's like mix of water and milk. Where the milk starts and where the water starts,
Right.
You don't know. It's the same. In a real sense that science itself cannot be separated into small boundaries.
Right.
And one of the prime example was an Indian scientist, Sir J.C. Bose. He was a biologist, he was a physicist, he used to make equipments. So the small boundaries, what we confine ourselves, chemists, physicists, biologists, mathematicians, they're artificial boundaries, they are made by mortal human beings like us. In science, actually, there is no boundary. Science is a single discipline pursued by curious minds. So that was the first question. Second question is that radiosensitizers, is it a final cure? No. Problem is that up to the time cancer does not have a clean and a single cure discovered. So that's why it's one of the hunting problem humankind is facing in the face of cancer. So if you remember what cancer actually is it's a divide cell without any control. So when we were, let's say 20 years, 30 years back, the case of cancers were not so much. How it has suddenly increased. So it's something to do with the lifetime of the people. Now with the modern facilities and modern treatment, people have a longer lifetime. So your cell gets old and then your DNAs get damaged and somehow it starts to divide uncontrollably. Problem is that up to the day, there is no single cure. So you say of radiation, you say of chemo, none of them is single cure. And many of the cases, drugs, what you use for treatment of cancer do more damage to our bodies. So many of the people who gets cancer cured then dies of secondary illness caused by these cancer drugs. So yes, you are right that all of them are in the prediction phase. None of them has been tested and it will be a still long way to a tangible cancer cure to come. So these are just very preliminary things which is going on. Third thing is that you asked about quantum computers and artificial intelligence. So this is just in the infancy of the thing. Quantum computers has just arrived. Many of the people even doubting its efficiency.
Right.
So many of the times, it's saying that it's faster than the classical computers, but many of the cases it cannot compute, like it cannot compete with a very efficiently written program on a classical computers. And don't forget that present day computers are very fast. Like these days, even mobiles have 5-6 GBs of RAM. When I started my PhD, even in a desktop, even a workstation, you don't used to have 2 GB RAMs. Now in my mobile, I have 6 GB. So classical computers are very powerful enough, but artificial intelligence is surely taking over, because in many of the cases which were routine jobs, just by literature, so basically a big part of the research is actually literature survey to see what other people have done, and from there you conclude, you make your plans, you decide how you are going to do the experiment. So that's was used to be done by humans, and now because of the artificial intelligence, it can go millions of literature and find out what should be the most optimum strategy. It's still not foolproof. It's not more as efficient as human, but if it can reduce your number of from 1,000 journals to, let's say, 1 or 2 journals you have to look at, that's actually a big benefit in terms. So it saves a lot of human time. And it's always interesting that human time is actually very costly. It's the computer time is cheap. You can buy computers at a throwaway price, but human time is very expensive and very difficult to get. So artificial intelligence, I think, is going to come up in a big way in chemistry, physics, and all the discipline, and in our life.
Thank you very much. Another pleasure too that you were a student of Viswanath where I was at also. Okay.
Nice to know.
Okay.
Thank you.
Anyone can ask question, and please unmute yourself and ask question.
Hi, this is Supriya here.
Yes, Supriyoda.
So nice talk. I have some few queries.
Yes.
When you done DFT calculation using for this acylation reaction, do you consider temperature effect?
Okay. So first thing we need to consider that all this modeling. So John Hogwarth was a very famous oncologist. He made a nice comment that a model is a lie, which helps you to see the truth. So whenever you do modeling, you need to understand what kind of accuracies you are looking at. When I did the DFT, all quantum chemical calculations, when you solve Schrodinger equation, there is no concept of temperature in the Schrodinger equation itself. So that means they were done in 0 Kelvin. Now, these reactions were done, I think, in room temperature. At least few of them I remember they were done in room temperature. Now, in that case, how I consider the effect of the temperature? So I consider the effect of the temperature through considering the temperature effect on the free energy, but those equations are calculated using classical partition functions. So the temperature effects were considered classically, and that's what is done in any quantum chemical calculation. Whenever you consider temperature effect, they were always done using classical partition functions.
No, so I have a great chance to meet Professor Kendall Howe in Scripps, and he was talking about how we can, and his recent stuff, if you see his paper, I think last 5 or 10 years, some of the guy, he's now faculty in Pittsburgh, they have developed a, I think, temperature parameter incorporated in the program software. However, I'm not a computational chemist, so I try to understand a little bit of it. Okay, and second question is that I think the solvated electron, I think that lifetime of the solvated electron will be very less. So what time scale and how it activates the molecule or synthesized molecule you want to use? So what is the kinetics and the mechanism?
Okay, I would have loved to talk on that. I can talk on it for hours. That is my now current research topic. So just to let you know, they are very fast processes. That they happen mostly in picosecond time scales. So that's why they are very difficult to trap experimentally. But in present time, this transient spectroscopy experiment, basically femtosecond pulse probes, you can measure the thing, you can understand what the mechanism is going on. But to model that is not very easy job, because you have to model the bulk environment. And so how it happened that water, we know, is a very good electron trap.
Yeah.
So when the solvated electron first remains, they remains on water. And after some time, within the picosecond time scale, they actually get transferred into this other molecules, so the DNAs. And this transfer actually happens through a non-adiabatic processes. So here the standard Born-Oppenheimer calculations, what we do, where you can separate the nuclear and electronic degrees of freedom, that will not work here. So here the Born-Oppenheimer approximation breaks down, and due to the mixing of the nuclear and electron degrees of freedom, they just actually transfer from water to the nucleobases. But this rates, so the experiments has just come out. We just proposed the mechanism. So we just communicated a paper explaining how this mechanism actually happening. So it's still a very hot field, but yes, that's a very interesting thing to look at. And remember, for this kind of studies, you cannot use standard quantum chemical calculus. So you don't use a standard PCM kind of a solvation where water is like solvation is described as a dielectric quantity. You need explicit water molecules, and for that you need to do a QMM kind of a calculation. So standard PCM based studies will not give you anything.
Thank you.
Hello.
Hello.
Good evening, good evening, sir. I am Anushwa Shah. I just want to know if anyone is interested to learn the artificial intelligence, then how should one proceed?
Okay. First thing to know any of these, you have to know a little bit of programming.
Okay.
But don't get scared by programming, and don't get scared that the programming is an exclusive domains of computer engineers. Many of the best of the programmers I know who are actually chemists or biologists by training. I learned programming after my master degree. So I learned programming in PhD. So programming is nothing difficult. You can easily learn it. So first I will advise you to learn a little bit of programming, because many of the artificial intelligence things essentially means that you have to process a large amount of data. And this data processing cannot be done by hand using Excel. So you need to use computer programs which can deal with this large amount of data. There's a lot of tutorials available, and good thing is that there are free tutorials available. You can do a lot of online courses. Sometimes some of the universities also organize artificial intelligence courses. So that you can go through. But before that, I will advise you to learn a little bit of programming. Then you can do it yourself. Otherwise, you will just use the tools developed by others. You cannot develop your own tools.
What type of programming should I learn? It's some kind of advanced like Java or something like that?
Oh, these days Python is good enough for almost everything. To learn Python is so simple that it's almost like English language. So if you know English language, you can almost start writing immediately Python. Python thing is that it's become so popular, a lot of tutorials available, a lot of free codes you can get, and you can learn it yourself very easily from the scratch. So I would advise you to go for Python.
Okay, thank you, sir. Thank you.
Any question from anyone? I think no. Okay. Finally, we come to the end of this wonderful and highly informative session. I would sincerely thank to Dr. Achintya Kumar Dutta for giving us his time and efforts. Particularly, I would like to thank our audience for joining us and their encouragement. The fact that Dr. Dutta took time to enlighten us considering his busy schedule, increasing our interpreters to him in manifold, and we always look forward to hosting him once again. With this, I would like to end the session with a promise.
I want to get email ID of Dr. Dutta, you know.
To meet one.
I think it's with Partho, he can give you.
Okay. Partho will get it. Okay.
Thank you very much for the kind opportunity.
Right.
I'm very happy to present my work in front of you. Please be safe and be well. Thank you very much.
You also be. Okay.
Bye.
Okay. Meet you again.
Okay. I collect the email ID from Partho. Okay.
Yeah.
Thank you.
Bye.
Okay, Dada.
Okay. Thank you very much for them.